Good morning, everybody. This is the first session of the Tuesday morning, so I'm actually super excited to talk to you today. I'm going to be your tour guide, your jockey, for the next 60 minutes to talk about an introduction into VXLAN. This is a 1000 session, so it's meant to be an intro, but I have a tendency to go a little bit more advanced. I'm going to do my best to keep it balanced, but I want to give you as much information as I can. And really the key word there is give. I want to be able to give you a lot of the knowledge, a lot of the things that I've learned through testing, configuring, looking at packet captures, but understanding the need of VXLAN. But there's a bit of a story, so just bear with me to talk about why are we here. There's always a why. Why did you come today, right? Why did you want to learn about VXLAN? So my name is Richard Lacone. I'm a principal technical marketing engineer for the Data Center Networking Business Unit. That's a mouthful. Working at Cisco Systems. I've been working with Cisco since 2001, so I probably look a lot different than I did when I was hired, right? But because of the experience, it's interesting to see how technologies have evolved. Looking at certain things, when I started out, it was DSL, DSLAMs. I'm going to be dating myself, CD-ROMs, Windows NT. And then we've kind of evolved much further than that, right? But I'm sure you probably remember that. So what I'd like to do is give you a little bit of housekeeping rules. I'm sure you guys are all aware of the application here. I'm going to do my best. I think it'd be challenging to answer questions live because I have a lot of material and I'd like to get through that. But I'm going to be standing here after, so I'd be more than happy to entertain your questions. But if you have ideas later in the week or later, please feel free to subscribe to this channel and then go ahead and I will be monitoring these for the next 2 weeks. So we can kind of build some kind of conversation and like to get to know you how you're using VXLAN. This is the session abstract. All of my slides are like this. Kidding. Can you imagine that? And I'll read every word. No, I wouldn't do that. But the main thing is the agenda, right? We're looking at about why are we here? And this is the kind of the discussions and the topics, the sections that I want to kind of go in this sequence to really bring the story together. Because I think that's important, is for you to understand why we're here and what we did and what we're able to do with VXLAN. So I'm going to pull you guys here and there for a couple just to kind of get an understanding. The first one is, how many of you out there still have spanning tree enabled in your networks? Quick show of hands. Wow, look at that. Cool. How many of you out there are using VXLAN in production environments? Quick show of hands. Okay, cool. So I think that this will probably, for some, a refresher, maybe just some other information you'd like to kind of gain from this topic. But I think it's interesting to understand, again, the technology that we're talking around virtualization. So before we can understand why the network needed to change, we need to understand how the application architectures were evolving. And if you think about it, it's kind of like a dance where servers were kind of leading the networking team with the dance. They were kind of always server virtualization, et cetera. But when we go back in time, how are these applications written? Mainframe servers, big bare metal compute servers, running monolithic applications. What did that mean? Single-threaded, single core, probably isolated as a single point of failure, but it was a big beefy box, big beefy system. And the way these applications were written were based on the CPU cores and how the business logic was rendered from the users, and they actually were there to kind of drive that level of compute power based on those requirements. But these really didn't have that kind of openness to scale beyond that particular data center or enterprise. It wasn't meant for that heavy-duty scale. And then as you think about what we've seen happen over time is the need, how can I take that physical compute piece of hardware and compartmentalize that into multiple virtual instances that have their own dedicated CPU, compute, memory? And that's where we saw the evolution of these web applications. Now, instead of having 20 servers and a few racks, I can have a single server with 20 virtual machines. And what does that give me? That gives me extreme level of portability and agility. Having the ability to scale and drive some of these requirements to understand that level of communication. Now I don't really have a single point of failure. I have multiple virtual machines that I could spin up in different locations for geo-redundancy, because I want to make sure I don't have any kind of downtime for my applications and for my users. So if we fast forward from that, what do we learn from the application virtualization? And something that we see much more often today is the world of containers, microservice-based architecture. And this is where we see, and the reason I'm talking about these evolution of application architectures, because the network was kind of fixed. The network had to evolve to match this evolution. Would you guys agree? And so therefore, we've seen, because of server virtualization, it increased a big load on the physical networking infrastructure. So we had to evolve. And so when I asked you, who out there is using Spanning Tree? You're probably very familiar with this diagram, right? Layer 2 in the access, layer 3 for your distribution to your core. Dual uplinks, one's active, one's standby. What do I have? A Spanning Tree root that's active and a Spanning Tree root that's distribution that's standby at those particular levels. What this did, though, is it introduced a couple of things. Spanning Tree was there to prevent loops, right? It was a loop-free topology algorithm that we were all there. And there was ways to kind of get around things. There's multi-spanning tree, PBST, PBST plus, rapid, just for convergence, topology change notifications, MAC flushes, because we had to understand, when a Spanning Tree loop occurred, how do you troubleshoot effectively? But how can I leverage both of those links? And if I'm paying money for dual ports to my distribution switches, but I'm only using one, that's not very cost effective. But that's essentially the network that we had with classic Spanning Tree. And then we moved along to something more where I could prevent that loop-free, where I had to have Spanning Tree using something called virtual port channel. Who out there has VPC configured in their networks today? Absolutely, everybody. And that's what we look at with multi-chassis link aggregation groups. The ability to have both of my uplinks running in parallel to be able to prevent that limitation of a loop and have that capacity and bandwidth and performance and reduce latency, et cetera. And I think that's important to see how we've evolved. But you still had Spanning Tree in the background as a fault containment algorithm. Not only that, is you were limited to 2 switches, correct? A pair of switches. You were typically limited to that. So it wasn't really a scale-out architecture. It was more of a scale-up architecture. So we still, as we try to evolve and match the evolution of the application architectures, there is still much work to be done. That's why we look at the invention of the Clos networks. Now, we're going into a little bit of history here. Charles Clos, a French engineer, scientist that worked at Bell, actually looked at how we can use patch panels and plugging in to create something that has 3 different stages that can give me an ability to scale out, to reduce the latency and have more deterministic traffic pattern and characteristics to go from leaf to spine back to leaf. And I think that's important when we're looking at these kind of stages. And what it does is it reminds me of a chassis switch, where your input stage is your ingress line card, your middle stage is maybe your fabric module, and then your output stage could be your egress line card. That's very much the analogy when you start looking at these Clos-based architectures. Now there's 3-tier Clos, there's 5-tier Clos, there's Butterfly, Dragonfly, there's all types of different Clos-based architectures. But this is essentially where we started to pivot from that 3-tier architecture to maybe a 2-tier leaf and spine architecture. And this became to what they call a folded Clos, where you have leaf, spine, back to your leaf. So deterministic hops and latency between that traffic characterization. And what we saw here is the evolution from north-south traffic, client-server traffic, everyone just going out to the web and coming back for requests, et cetera, to more of an east-west traffic algorithm, right? Because that's what virtualization started to give you, the ability now to support things like vMotion. But I needed to support layer 2 adjacency. So how could I do that with my physical infrastructure? If I still wanted to leverage things like layer 3, I didn't want to always have to trombone and hairpin back to my distribution layer switches. How can I actually take advantage of that? So what Cisco did is Cisco, many moons ago, created a technology called Fabric Path. Does anybody have Fabric Path in your networks today? Cool. So Fabric Path was Cisco's first overlay technology, right? We supported something called MAC in MAC to be able to use VXLAN as our data encapsulation, but use other protocols. Or a form of, it was an attempt to be VXLAN, but it was a MAC in MAC data plane, and we used ISIS as our control plane. Now, for its time, it was actually really good. Very easy to configure, understanding, host interfaces and network interfaces, and you can still see here, though, we had this layer 2, layer 3 demarcation. So there were still opportunities to kind of move towards to get us more agility and more capability to support virtualization environments. And that's really what it is with virtualization, is to be able to spin up stuff quick, move them quick, and scale. And a lot of the times, too, customers said, I like this, but it doesn't interoperate well. It's proprietary. I want something a little bit more open in standards. So what did we did? What the industry did was they developed something called VXLAN. So you can see the evolution of the architectures, the applications, and the networks. Spanning tree, VPC, Fabric Path, to now VXLAN. But now, you notice I'm just saying VXLAN. I'm not saying there's a control plane here. Because VXLAN, when it first came out, the control plane was something called flood and learn. Ethernet, right? Broadcast. If I need to find out where you're at, I'm going to shout. And then everyone's going to listen to me, and they're going to flood out, and they're going to give me your location. That was the whole mentality of this type of network we can introduce with the flood and learn mechanism for the control plane. But if you can see how we transition through the slides, now I'm using, the red was layer 3, the blue is layer 2. Now I'm able to build a fabric over a layer 3 network. And what I want to have is transport independence. How can I support layer 2 and layer 3 over a layer 3 network? And that's what we're kind of showcasing here. So there were a lot of challenges, as I mentioned before, when we looked at these different architectures, from scale, unused links, redundancy, efficiency, not the best type of forwarding. And then there's different, kind of costs that are associated with that when you start looking at these different technologies. So we needed to kind of understand what were those problems and those challenges with the legacy architectures and how could we evolve. So there was the need to actually introduce this concept of network virtualization overlays. Now, overlays are not new. They've been around for a long time. GRE, IPsec, MPLS, Atom, any transport over MPLS. You have a lot of different overlay technologies where essentially what are you doing? You're really taking that packet and you're putting an additional header on top of that, encapsulating that packet. And now you're looking at that particular piece of information versus the other packet that was kind of originally encapsulated. So what I want to do here is actually look at the taxonomy to understand what are those things that we're looking at and classifying by every different terminology to really see where we're taking this to that particular use case to understand overlays. So then we look into the overlay services, we have these different buckets. Because what we want to do is be able to support layer 2 and layer 3. You should be able to support things like layer 2 services. As I mentioned before, you may have an application or some type of server that requires this layer 2 communication, non-IP. There's lots of those still out there. And then you have layer 3 overlay services, which is strictly routing. But then you actually want to blend these and have something more integrated, like integrated routing and bridge, IRB. And that's a typically overlay services that you get best of both, layer 2 and layer 3. And then from there, what we see is the tunnel encapsulations, as I mentioned before, the wrappers, the additional packets that went inside that to understand what is it I can do for a layer 2? Can I give you something like Q&Q, where I can actually have a .1Q and another .1Q to give you more isolation with your CE and your PE in a service provider environment? Customers are using that in different types of architectures. And then you have something like network virtualization overlay, the standard that IETF actually published with the RFC 7348 to understand what that looks like. And then from a layer 3 VPN, that's what I was talking about before with the tunnel encapsulations, things like GRE, generic route encapsulation, MPLS for layer 3 VPNs, and things like Lisp. So these, again, have been out there for quite some time. And then let's talk about the need for what we call an underlay. And I'm sure it's interesting when you start thinking about the foundation of a layer 3 fabric being built as an underlay network. that can actually support overlay services. So I visualize that picture in the beginning of that server as kind of like that physical box, but then having virtualization over that. So the underlay is like your physical network. We're able to extend communication between your VTEPs, virtual tunnel endpoints, and we'll talk about that in some upcoming slides. But the underlay network had support for 2 different routing protocols, some IGPs. Typically, you can support underlays over layer 2 fabrics with maybe spanning tree or something like ISIS, if you're familiar with that. Or you can have more of a traditional layer 3 IGP like OSPF, ISIS. Maybe you're looking at something with eBGP. But this is where you would have those type of protocols configured in your underlay fabric to be able to support communication between these tunnel endpoints. And that's what's important. But now when I talk about the tunnel encapsulation, the underlay, the overlay services, what is the control plane's role? Because there's a control plane element to this. And you think about a box, a switch, there's a route processor, there's a CPU. That's kind of the control plane complex versus the fast plane, the ASICs, which is going to be more of the data plane. But what are the responsibilities of the control plane are really to look at how do we learn, whether it's locally learning, how do we learn remote? And then what do we do with that information? How do I share what I've learned with you? How do I share with what I learned with you? And then we can have this level of distributing the information based on the location of my devices, my endpoints, to different people or different entities in the network into the fabric. And that's important. And so not only that, as we do the distribution of our routes, but also our peers. When I discover peers, I want to make sure I can communicate that so we have an efficient knowledge of who's connected where, behind what. Because there's going to be different peers that will have different networks behind them, different hosts, different prefixes. And that's what's very important there. And as I mentioned before, the data plane, this is the role of the data plane, right? If you look at the hardware of a box, this is what it's actually going to do. But the data plane for the VXLAN, or this virtualization technologies, is looking at the encapsulation. The ability to take a packet, encapsulate it, move it through the fabric, get that packet to its receiver here or destination, de-encapsulate that, and then send it on its way via classical Ethernet. That's typically how we looked at the communication from an encapsulation, de-encapsulation. And then we have unicast forwarding for layer 2, layer 3, but we also have multi-destination traffic, right? What's a good protocol for multi-destination traffic? ARP, right? ARP, when I don't know where somebody's at, flood and learn, or how do you feel it, I'm going to broadcast. And what I do is I send traffic of all my ports. That's multi-destination traffic. Or if I don't know a particular unicast address, I'm going to broadcast as well and flood the network. So those are mechanisms to understand how we had to treat different types of traffic characterizations. And so I'm telling you all this to get to this point here. We're talking about VXLAN, right? So VXLAN is, if you check out the RFC 7348, there's multiple companies that worked on the program of the VXLAN technology, which is really need to define these overlay networks. And if you look at it, it's really more of an informational standard. It's not true ratifies, it's informational. But we've all become the de facto using this, and the reasons why is it gives you a lot of cool capability. For one, it's a MAC and IP technology. So I'm using MAC and IP to have that kind of ability to carry that packet across my fabric. Why is that important? Well, there's a couple of things in here. As I mentioned before, if you think about integrated routing and bridging, IRB, the ability to have blended services for layer 2 and layer 3, that's my transport independence. I have independence of how I carry that traffic over across that layer 3 fabric. For layer 2 services, a MAC VRF, or layer 3 services for layer 3 VRFs. But also, now that I'm using MAC and IP, I get something really cool with the UDP encapsulation. So if you guys remember the packets, and I'm going to show you an example of what the packet format looks like, UDP encapsulation gives you the ability to have a level of traffic entropy. What does that mean? Traffic entropy is the ability now to look at multiple fields into the source port to be able to, I can efficiently spray my traffic equally across multiple links. Because now I can do things like equal cost multipath, where I can have, say, 4 links in an ECMP group sending out, so making sure I have that, I can leverage all of those links simultaneously. But what I don't want to have is polarization. Imagine if I'm sending 100% of traffic going from one across 4 different links. But if I look in my show interface counters, I can see 100% of that traffic only traversing over one link. That happens sometimes because there's no randomness in the packet for the ASICs to determine and spray across evenly. So with traffic entropy now, we can actually hash based on a 5-tuple to be able to give you that level of entropy to spray across these links evenly. And this is important, even when we start talking about AI fabric networks, the level of traffic entropy there. Not only that is it gives you that flexible namespace for segmentation. If you think about what we had before, what was before VXLAN? VLANs. VLANs was a 12-bit identifier that gives me 4,096 capable VLANs I could support on my switch. Now with VXLAN, I'm using 24 bits, so I have a flexible namespace, and what that can do is that gives me actually 16 million segments that I can actually support now with the VXLAN encapsulation. Does that mean I can support 16 million segments on a switch? No, it won't support that. But in your fabric, it's going to be able to actually determine what you can actually, so that there's no collisions because you have duplicate VXLAN segments across your fabric. So it's important to understand that. Now, when we start looking at the underlay taxonomy, let's look at the pictures here of what we're talking about. We have these edge devices, and these edge devices are what we call in the standards network virtualization edge. And really what this is a role of a different device. It could be a switch, it could be a router, it could be a virtual switch. And really what its job is to really encapsulate that traffic coming from your Ethernet and then shipping that into a VXLAN packet and sending that over to the fabric. And I have different endpoints, as I mentioned, virtual machines, containers, compute services running on bare metal. I have those there. And so that's what we leveraged, and we looked at kind of that equal cost multipath, the ability to have multiple paths, and send those to different destinations based on that traffic entropy. And this is the underlay. So this is how I build that underlay to establish communications across my L3 fabric. Now, the important thing here too is to see the shadow. You see the shadow here that's running on top of the underlay? That's the overlay network. So if you remember we were talking about the taxonomy, we talked about the need to build a layer 3 fabric as the underlay and then generate an overlay and create that to use our tunnel encapsulation, because really what happens is these endpoints, they could be physically in different locations, but leveraging the technology here, to them, they can appear to be sitting right next to each other, but they could be in different racks, in different pods, and in different data centers. And that's what we get the ability to leverage using a tunnel encapsulation like VXLAN. So VTEP is VXLAN tunnel endpoint. We have the identifiers. Instead of a VLAN, it's called a VNID or a VNI, VXLAN network interface. And this is essentially what we're looking at when we talk about the role of the VTEP, the encapsulation mechanisms, the ability to take that classic Ethernet frame and ship it out to a VXLAN packet. That's the role and the functionality of being able to use that VXLAN role for the VTEP. And so what that allows me to do is when I can bridge when I need to, or I can route when I want to. Based on that layer 3 fabric, I have that information to support layer 2 VNIs and also layer 3 VNIs. So the frame packet. This is actually really, really cool. If you've ever done any types of Wireshark or packet captures, you can really see this kind of looking at the packet from how it's built and constructed. But let's take a look and see what we see in that VXLAN packet here, what that looks like. Because you can see here there's a lot of different values, right? You can see that we have our traditional Ethernet frame, stuff that you're familiar with our inner packet or inner MAC source address, the inner MAC destination address, the optional .1Q header if we needed that, and then we have our original Ethernet payload. Now what we do with VXLAN, if you look at the red, the VXLAN shim header, now we can start encapsulating that into VXLAN. And this is where I have a well-known destination port. This is reserved for VXLAN only by the INA 4789, and that's where UDP comes in. That gives you that level of traffic entropy. And then I have my outer IP, source and address, destination addresses, my optional .1Q, and then my outer MAC address as well. That's the VXLAN packet. We're going to look closer into this moving forward. But there's a cost that's associated when you start using the Ethernet with VXLAN. What do you think it is? MTU, right? You need to factor what that looks like. And because now we're looking at that additional MTU that we've incorporated on the Ethernet fabric, we need to make sure that the network can handle that transmission, because VXLAN is not going to be able to do segmentation or fragmented packets. So it wants to keep these packets whole. So our recommendation is, for you're looking at VXLAN, and I'm sure you're using that, you want to be able to make sure the NIC can support that level of frame. So most NICs today can go up to 9,000 MTU size. On our switch ports, we support 9216. So those are the size that we would actually recommend. Just crank those up to support this level of transmission across your fabric. I guess the only caveat here, if you're going over an SP or a service provider network, sometimes you want to make sure they support that level of MTU. So that could be something to be prepared for and document, and just when you're at that time, if you're traversing over a service provider environment, understand what the MTU requirements are. Now, when we look at the VXLAN packet, let's look at the red box here, and that's the VXLAN header. Really, there's only two pieces of information that are really important and significant for the VXLAN communication. Now, if you look at the very, very top, if you read the standard, all these R's are zeros. And really, these are just ignored. The only significant bit is this I flag. And what that I flag does is it tells the receiver that there's a valid VNI present. Everything else is zero. So that's kind of letting it know that there's a VNI coming, and this is where we see that 16 million segment flexible namespace coming in with these 24 bits. Remember, as I said earlier, VLAN was half of this, and that's why we had 4,000. And then we have this other reserve. So there's two reserve blocks, but really the more important pieces are the I flag that I mentioned before, and then the VNIs. That gives you your flexible namespace to be able to support the additional scale. So that's what's important there. Now, to configure it is pretty straightforward, right? If you configure this via the CLI, you would configure a VLAN, and then under that VLAN, you would map it to a VNI segment. And that's what the CLI looks like with NXOS. Now, what I want to do is, when I'm communicating across my fabric, because I'm using a layer 3 routed fabric, really this is kind of the important pieces of where I communicate and where I actually use that communication to send my traffics to source and destination, using the outer source address and my outer packet here. So for IP UDP, these are the areas that I look at. And as I mentioned before, that UDP header comes into importance here, because this is something that's different from a GRE overlay technology. GRE didn't have this UDP encapsulation for traffic entropy. So what that does is I take that original Ethernet frame, and I have the ability to use the 5 tuples here to create a hash based on that parameters. This thing's slipping off of me. So what we see here is actually the ability to create, I use my destination port 4789 here, but then I have a randomness. I build a hash into the hardware by the ASICs and actually create a randomized source port to give me that level of entropy per traffic. Sorry for this little. Thank you. Thank you. So UDP makes it simple, and it makes it possible for this hashing to take place. So we're talking about the frame of the VXLAN packet, right? We're not talking anything EVPN yet, because VXLAN is a data plane encapsulation technology. But what it did is it had something called flood and learn. So this is something that we've kind of evolved away from, leveraging this kind of, for multi-destination traffic, there's 2 ways I can support this in a VXLAN environment. And the way I can support it is using something for maybe ingress replication or multicast in the underlay. Because what I want to be able to do is send that packet to my remote copies. And so what I would have to do is have the ability to take that VNI, the layer 2 VNI, and map that to a multicast group. And a multicast group is going to go ahead and send that out to the receivers that are interested for this multi-destination traffic. And so that's what's important here, is when you see what's that requirement. Now, I have a lot of hidden slides in this presentation that go through this packet walk. So those are there for you. I'm just not going to spend time on it because this isn't as really relevant, but it's there to educate why we needed a control plane like EVPN, because this is the way we actually used things when VXLAN first came out. So if I go back a slide, When we look at ingress replication or head-end replication, what does that mean to the networks? And this is okay for a small data center, right? Because what you're doing is that ingress VTEP has to send multiple copies based on my receivers. If you guys are all interested, I have to send you a copy, you a copy, you a copy, you a copy. Eventually, that starts putting a load on me. And if you think about how much traffic that is across the network, something you can see here for an example of maybe 10 meg of bump traffic, based on the number of nodes, that's going to be your, what you're going to see, that bandwidth consumption across your fabric. So there's a lot of inefficiency there, or maybe there's something you don't want to waste your resources on. But that was one of the mechanisms for multi-destination. But what we saw here is, what did VXLAN give us and how did we get here? Right? We can see here that we took advantage of scale. Now we can say from 4,000 VLANs, we can go to 16 million segments. For VM mobility, now we have the ability to not just keep that VM into one location, we can actually do a vMotion and support that because we have layer 2 adjacency across my layer 3 fabric. Who out here has done vMotions before? Right? It's actually something very, really cool because it's important. If you see this server is actually starting to kind of fail and have resource issues or maybe kind of crash, you can take that virtual machine and move it to another appliance seamlessly. That's pretty cool technology. And we leverage things like ECMP, equal cost multipath, to be able to take advantage of those links and be able to spray across efficiently. That's important, what we can do. And there's no more boundaries of being able to support this, and we have a secure multi-tenancy, being able to use VXLAN as that encapsulation method. But this isn't it. We weren't done here. There was a need to be able to take advantage and evolve the VXLAN technology. That's why we created a control plane and leveraged what was already there in existence with EVPN. And what EVPN does, as it's been around, this is actually a true standard. It's not informational. You have different types of data plane encapsulations, MPLS, provider backbone bridging. And then you can see what was invented here for VXLAN is network virtualization overlay that's in this draft. And this is what we actually saw of how we can take advantage of the EVPN control plane, which is really built on multi-protocol BGP principles. And with BGP, that's really the protocol that runs the internet. Very mature. How can I get layer 2 and layer 3 information to you? How can I share and distribute that? My MAC addresses and if they're in a VRF or if they're not in a VRF. I think it's very important to understand that. Now with this, there came a different set of routes. And then you can see here what we had. We had different route types. And the route types here were built for different reasons and different purposes. The main route types that we're kind of associated with and we want you to be most familiar with are route types 2 and 5. Route types 2 are how my VTEPs communicate with the route server to be able to kind of tell you where those MAC addresses kind of reside based on what I've learned. So route type 2s have the ability to send MAC as a lowest common attribute, or MAC and IP, if I have the MAC and IP address. And then route type 5s are more of my prefix routes. If I have VTEPs connecting to a different external network, I have the ability to extend the prefix only via that route type communication. And these are advertised via BGP formats, something that we've already know that's been tried and tested and proven, the network layer reachability information, and we send that out. So when we start looking at multi-protocol BGP, let's just build this out. There's things that we talk about, right? We leverage the VPN address family to carry that, address family information and subsequent address family information to carry layer 2 and layer 3 across the network via these control plane updates. Remember those blue boxes, data plane, control plane? This is the control plane here. BGP EVPN is taking advantage of this stuff. And we leverage technologies like VRFs, virtual routing and forwarding, really taking that ability to have my global routing table and compartmentalize that and virtualize different pieces of that to segment based on my tenant. Based on you, I have your routes. Based on you, I have your routes. And so you want to make sure that's fully isolated and that supports things like overlapping IP addresses. If there's an acquisition, maybe there's a subnet that's already been used by the company that you acquired. How can you make sure those can coexist? You can slap a VRF around those to make sure that those networks can get to and fro. But how do I make things unique? Because what I'm seeing here is when I'm using these technologies and I'm using virtualization, and if I'm using some kind of overlapping IP addresses, I want to have the ability to distinguish what that looks like, and that's with my update, and that's what's called a route distinguisher. And really, a route distinguisher is what we do is we take that route distinguisher and then we add the VPN prefix, and that gives me that unique characteristic to differentiate from others into my routing protocol. And what I want to do is the ability to import and export based on your VRF, based on what you need. If you need access to these services, I want to make sure I can import those to you and you can export them back to me. But if you don't, I don't need to. You can be selective on what you're learning. So it's very, very intelligent and efficient in how that's working. And that's kind of what the example is showing here is you can get that information based on how you propagate with the route distinguishers and carry that over into that BGP NLRA kind of communication to this next hop. And that's essentially what you're doing here. So what does EVPN in the data center bring you? It gives you a lot of stuff. And I think there's a lot of cool capabilities that it moved away from the flood and learn principles that now we can have something called an Anycast IP gateway. So imagine your leafs, your top of rack switches that are on different racks can all be a gateway for a virtual machine. How does that work? And then the Anycast gateway, the closest one to the VM is going to be the one that replies. So that gives me flexibility, agility, and redundancy. If I had one gateway or a pair of gateways and one of them failed, then I'm kind of stuck in a situation. But now I have a concept of Anycast IP gateways through EVPN. Not only that, is I have the ability to have more secure kind of authentication mechanisms with BGP. If I just walked into my network and I had a new Tor and I plugged it in and I wanted to peer, with BGP you have to authenticate. You can actually configure that now, so I won't be able to kind of hack and compromise the network. Not only that, is I can do things like ARP suppression. ARP suppression is very cool because the VTEP has in its ARP cache information of the endpoints. Instead of having to do a flood and learn or a broadcast or bump traffic across the fabric, it can actually respond on behalf of that destination. That's different from a proxy ARP, but it has the ability to respond and have more efficient use of the fabric and be able to locally learn and give that information to the requester looking at an ARP. And then we can look at ingress replications with flood lists, et cetera. So what I want to do right now is spend time on VXLAN, BGP, EVPN, just in looking at how it works under the covers. Pop open the hood, and let's see, when we have an overlay network, how do we learn with each other? And so what you see here, as I mentioned before, there's different routes, route type 2, route type 5, and this is the way we communicate. The spines are configured as route reflectors, right? The leafs are going to be your route reflector clients. This makes it more efficient than having to create a full mesh IBGP network, having to peer with everything. This is now more efficient because I can actually, based on what I learned, I can take that information and send it to my route reflector, and then my route reflector can reflect to the other VTEPs that want to learn about it. So that's how that works. So it's more efficient than having everything fully meshed in that environment. And these are the routes here that we look at. So when we're looking at this, let's stick with this example here. Okay, I want to give you an example of these host advertisements. Now we have 3 hosts with their MAC addresses present. So what Leaf's going to do is it's going to say, I'm going to send, based on my host, I know that there's a host A sitting on the Leaf 1, and its MAC address is 3001.1101. What I'm going to do is take that information and sending up to my spine, I'm going to start building a table. In that table, I can see route type 2, I can see the MAC address and its length, and I can see my layer 2 VNI, the VXLAN encapsulation of what that looks like, and then my route target, and then my next hop. So the next hop is always going to be that leaf where it's sourced from. That makes sense? And then we do the same thing for the next thing. The next leaf 2 is going to send its route 2 type update to the spine and be able to build that out accordingly as well. It's established its MAC address there, so it's going to the route reflectors. It's sending the information, and then route reflectors will propagate it back down to the VTEP so that everybody knows this communication, and it does this intelligently to do that. And so again, I take route type 2, and then I do the same information, and I'm building that table of my endpoints via the MAC address. So now BGP is carrying MAC address information from the VTEP to the route reflector. And that's what I'm doing, carrying that information. I won't, sequences here, this actually increments when there's a MAC move. We're not going to really talk about that today. But this is kind of what you see for route type 2s when you start traversing and carrying those messages and propagating from your VTEPs to your route reflectors that are configured on the spine. Now, as I mentioned, there's another route type 2 out there. And then this is what's going to see here is for this route type 2, you have a single layer is carrying the MAC information and a route target for the MAC VRF. Now, if I look at layer 3 VNIs, layer 3 networks, now I have the ability, in the screens before, I was only showing the MAC address. Now I'm showing MAC and IP. So now what I want to do is I want to start building more information in that route update. Maybe I want to give you that longest prefix match, my /32, my host route. And that's exactly what I'm doing here. It still comes in as a route type 2, but now I'm filling out the fields. This is the new fields that I filled out. Before you saw I had the MAC, the L2 VNI information, the autonomous system, and the route target. Now I have the IP address, its length, the host route, and I have an L3 VNI that has the L3 VNI identifier, the autonomous system, and this becomes the route target as this combination, that uniqueness, what we talked about earlier. And again, the next hop interface is going to be the source, the VTEP here. So this is how I'm building that information via EVP and BGP with route type 2s for layer 3 VNIs on host advertisements. Same thing as I walk through this, take that host B, I plug in and I populate it with the 192.168.10.102, and I specify its L3 VNI and its route target, and the same thing for leaf 4. So I'm building these tables out for layer 2 and layer 3 to be able to make sure that I have the communication and you have the ideas of where everything is located. That's what we're showing here. We're building that level of information. Now, what we do here, as I mentioned before, EVPN was primarily used initially with MPLS. So that's why you see these MPLS labels. Label 1 is the layer 2 VNI. Label 2 is the layer 3 VNI. And this is essentially what we're doing is we're actually sharing this information as we go across the fabric and how we're communicating, updating these messages when we're advertising these routes to the route reflector that's going to be reflected back to your client. That's what's important here when we start that level of communication. So those are route type 2s. What about IP prefixes? Those are subnet advertisements. What if I have different networks? Same thing. Now, all I'm seeing here now is instead of having MAC address information, these are now route type 5s with my IP address and its length. You can see here now it's not a host route. It's more of a /24 in this example, but I have the layer 3 VNI information and I have its next hop interfaces. So I'm building this because I want to make sure I have the ability to detect maybe a silent host. And I want to be able to see I can glean from that IP address and ARP from that local VTEP that's connected to that destination. But I can use this information to build route type 2s for MAC address, MAC and IP prefixes with route type 5. I'm hoping this makes sense. Yes, question. So the question is, yes. The spines are the route reflectors. So the spines are always configured. Only do a pair of them. We only usually do a pair of route reflectors, and those will distribute out to your VTEPs. The other spines aren't participating in that. So it's really this, you can kind of elect your pair of route reflectors. That's the question. And so you don't have to have all spines configured as route reflectors. You can have a pair if you wanted to. It makes it simpler for your configuration and the state that needs to maintain it. If you wanted to have that, you can configure maybe more than that, but typically we see a pair of those. So route reflectors and rendezvous points on the same spine switch, okay? Now let's look at a packet walk. Because what I want to show you here is we looked at how the control plane is built, how that information is built. Now, how does that packet traverse through the VXLAN fabric? Now, host A wants to communicate with host B. So these are the two hosts, right? And now I have VTEP1. So remember those yellow circles I had in the beginning? Now I've kind of made them a little bit bigger just so you can see what's configured on there. What are their Anycast gateway addresses? What's the MAC address? And then where those residing here. So this is the communication what I want. And remember now, I'm not using the VLANs, but I'm using VNIs. So when host A wants to communicate with host B, it's going to go in and generate traffic, right? It's data traffic. It's going to send its source MAC address here, the 3000.11.0.1, and this source IP address. And it's going to say the destination IP address, I want it to be the destination IP address of host B. And so what happens here is when the VTEP sees that packet, it's going to go ahead and receive that packet, and it's going to look into its table. It's going to look into its ARP cache Do I need to flood? Do I need to kind of send multicast packet to get that multi-destination out there to learn this? It's already there. It's totally populated. That's why I have here in this corner that the ARP cache is populated. Now, when I do this, what happens here is the packet is received on that particular VTEP because the VLAN is mapped to that VNI, and then I can kind of see how they get to that network based on the tables that I just showed you how I built. And so what the VTEP does is encapsulates that Ethernet packet and puts it into a VXLAN packet. And now that packet is going to be transported over the VXLAN fabric to VTEP2. And what you're looking at here is as you're going through this, you're understanding the underlays, the overlays, how these packets kind of, the values change, but what stays constant are your outer headers. Now your underlay network is going to route the packet based on the outer IP header. That's step number 4. And then step number 5 is when VTEP v2 receives that VXLAN packet, and then what it needs to do is it needs to look in its table. And so the VTEP2 performs a layer 2 lookup based on that layer 2 VNI 3001. And based on that information, it has the MAC address. It has the IP address, the L2 VNI, and its next hop. And then the VXLAN packet is de-encapsulated. And then it's because of that local mapping in its table of that VNI to the VLAN, it's going to go ahead and ship that out an Ethernet frame back into this host. So the hosts on the side never see this. To them, it's just an Ethernet packet on the wire. They're never going to see all this stuff happening over the overlay. And that's what's nice is it's very seamless, right? If you look at the hosts, they're just going to see packets as if they were next to each other. And that's what the communication looks like through a packet walk for layer 2 VNIs. What happens when we look at communication across different VNIs? So now what we're looking at here is communication, layer 3 communication. Now I have 2 different VNIs. Host A wants to communicate with host Y. I'm going from VNI 30,001 to VNI 30,002. Now what I establish here, because I'm using symmetric IRB, we didn't really talk about that yet, but I'm using something that gives me consistency where I don't have to over-configure my boxes to be able to use that as a transport mechanism for layer 3 communication across the VTEPs. And so those are for different tenants. And what you see here is now host A is going to generate this data traffic with its source MAC, but now I'm talking layer 3. So what needs to happen here is the layer 3 destination MAC address is the Anycast gateway address. So the layer 3 MAC address here is a DMAC of Anycast gateway that you see here. What does that do to the VTEP that receives that packet? It's going to trigger the route processor to say, oh, wow, look, I need a route. I need to send this packet and route out to that destination because it sees itself as the destination MAC address. So it needs to kind of kick up the routing algorithm and send that to the VTEP v2. So it does the same thing. It goes into its lookup table. When we looked at the host overlay advertisement and subnet advertisement, we're going to see here now, based on this longest prefix match, route type 2, I have the MAC, I have the IP, I see the VNI, I have the L3 VNI information, and I have its next hop at 200.2. So I have that level of information. So now what I'm going to do is I'm going to send that out. I'm going to rewrite the inner MAC address. So you'll see that here, the inner MAC address is going to be rewritten based on the NVE interface here of this VTEP here. And then VTEP encapsulate this Ethernet packet into VXLAN and then sends it to the VTEP v2 over the overlay across this VNI 50,001. And so it's going to send that information across that and use it as its transport. And then what you're going to see here is the underlay network is going to route the packet based on that outer IP header. That's how this overlay underlay works when you have a layer 3 routed fabric. Now, when VTEP v2 receives the VXLAN packet based on its destination MAC, it's going to perform that routing lookup, and it's going to look in the layer 3 VNI for 50,001, and it's going to determine that this packet is going to be mapped to this virtualization, this VRF forwarding table, VRFA. And so this is kind of what we see what takes place is through this packet, and you guys can look at these in your slides or your handouts and see how this packet, and I made sure that through the Wireshark captures, I'm matching the fields, just visualizing it differently. And then you can kind of see what the VTEP does is it de-encapsulates that VXLAN packet, it rewrites the MAC address, and then it sends it out to the Ethernet as an Ethernet frame to host Y. And so that's what we're kind of looking at here with the packet walk when understanding how VXLAN works with the encapsulation. So we talked about how the EVPN BGP builds the tables, right? We can kind of see when we go back how these tables are built with host advertisements, prefix advertisements. Those are built and those are necessary to send this communication for layer 2 transmission and layer 3 transmission. So that's the first and foremost thing we have to operate. So to your question, yes, the route reflectors are on the spines, that'll send them out to the VTEPs, and the VTEPs can actually send traffic accordingly. So that's what's nice about this is you can leverage, instead of using a flood and learn with EVPN VXLAN, when we had just VXLAN without a control plane, it was much more resource intensive onto your VTEPs, having to build multi-destination frames, multicast traffic without EVPN. So that's why you can see there was a need for VXLAN to have a control plane like EVPN to be able to transport more effectively, take advantage of things like ARP suppression, take advantage of things like secure multi-tenancy. And that's what we're looking at here with this kind of packet terminology and these packet walks, is to understand that. Is this making sense? Question. Yes. So the question is, if you're not using EVPN, you're using head-end replication, ingress replication, or multicast, the leaf should be able to perform ARP suppression. Now, the ARP suppression comes in with EVPN as a protocol. EVPN supports that on a per layer 2 VNI basis. So that's something you actually would configure under your layer 2 VNI. It'll be suppress ARP when you're typing that into your CLI. So it's really a function of the EVPN protocol that can actually support that. Because what ARP suppression is doing is it's saying, if I have that, as I mentioned before, if the VTEP understands in this ARP address that it has that destination here, it's going to go ahead and send that much more efficiently because it's building it from the EVPN table. So that's why I can actually send that. So what happens in a BUM is when I'm learning that traffic, when I'm actually sending a multi-destination packet, then the receiver is going to send a unicast packet back, the ARP response, back to the source to just let it know that it's there. So to your question, EVPN is needed for ARP suppression. With BUM traffic, you would have more, probably not the ability to do that level of suppression. You'd have to go over the fabric to learn, okay? So what did we learn here? We talked about RFC 7348. We talked about Ethernet over IP, the challenges what we saw with spanning tree, the challenges we saw with the flood and learn, the hairpinning of traffic, right? How we're able to not really support that level of traffic entropy, to take advantage of load balancing across equal cost multipaths. Not only that, is we were looking at more of a primitive control plane, right? We still use something like first hop redundancy protocols like HSRP, VRRP, GLBP. And then if you wanted to do something like virtualization, it was more or less over the top. It wasn't integrated with EVPN. Now what you see here is VXLAN and EVPN are tightly coupled together as a control plane and a data plane. And that's kind of the thing that you see here is when you look at this RFC, there's actually ability, now you don't no longer need spanning tree enabled because you're using a layer 3 routed fabric, right? So you've eliminated the need to carry BPDUs, bridge protocol data units. You don't need to configure BPDU guard, root guard, loop guard on your access or your VTEP interfaces because everything's layer 3. So I think it's important there as we start transitioning and evolving, we've modernized the fabric to match what the server world is doing in the applications. Because if you think about how we look in the industry, the server world is always faster than networking, right? Server worlds went faster. Now we're seeing GPU communication, and we're looking at, how does the fabric handle lossless Ethernets and congestion mechanisms, et cetera. But now we're looking at EVPN here, and you can see the endpoint learning is based on these BGP exchange, the route type 2s, the route type 5s, the MAC and IP. How are we learning that information from our route reflectors? I keep looking at you for route reflector. But that's exactly what we're looking at. That's exactly how we're building that communication and the database. Not only that, is we can provide a blended service offering, leveraging layer 2 and layer 3. We're able to take advantage of something called integrated routing and bridging, where over that layer 3 fabric, I can carry layer 2 services. And that's important because if you look at, you can probably do a vMotion with over layer 3, but VMware will support, they will say layer 2 adjacency is required for vMotion, right? Into your documentation, if you call their support, they're going to make sure you're using some type of layer 2 adjacency. So that's where you can actually leverage something like a VXLAN fabric to be able to carry that across the fabric and have that layer 2 adjacency in your network. And then we use something like this distributed Anycast gateway. This is really cool because now I have for every top of my rack switch, I can have for different SVIs a default Anycast gateway so that they can all be active for my particular VM, my container. And again, they're all going to be there, but the closest default gateways or the Anycast gateway is going to respond. So what does that do? Is that gives me better performance. That gives me better redundancy, better availability, and it gives me lower latency, right? Because this is actually a lot closer than having to go over here all the way back up to your distribution layer, then back down. I'm not hairpinning anymore. Layer 3 proximity is much closer. And we use this layer 3 VPN approach very similar to MPLS. And then there's much more than EVPN. There's many more technologies and discussions at Cisco Live. I would encourage you to attend, if you haven't already, Lucas Kratiger. He has a session just on packet walks. And he goes in much, much more detail. It's not an introduction section, but it's very, very rich with regards to packet walks over the multi-site and single-site operations for fabrics. Wow, that was a quick 58 minutes. I got a little bit of a workout. You saw me sweating. But what we saw here, there's a lot of good information here, material. Can you believe it or not? VXLAN came out in 2017, and we're still talking about it today because it keeps on changing. We're looking at how we configure it, and it's a hefty configuration. There's a lot of lines of configuration. For your Leaf on an NXOS, sometimes it's 500 lines of config. That's a lot to type. And on your spines, it could be 350, because your spines aren't caring about the VXLAN information. It just carries about the IP. If you notice that, the spines are just acting as your route reflectors and all your BGP information. The VXLAN is on the VTEPs. It's just tunneling over that layer 3 network. But you understand that there's a need to automate this, whether it's through Ansible, whether it's through Terraform, whether it's through different tools like our Nexus Dashboard Fabric Controller. You can automate this at much more point-click to get all those best practices kind of configured and incorporated. And that's what's important here. So these are the recommended Cisco Live sessions that I would encourage you guys to attend if you can. There's a lot of great information here, whether it's here live at Cisco Live Amsterdam or it's in your on-demand. These are great sessions to attend that you can actually learn and start building your knowledge and being more familiar, more comfortable to implement, to configure, to troubleshoot, to automate, and to be able to kind of move things forward. Again, if you have any questions, please use this chat, subscribe to it. I will answer my questions. My colleagues are in this room monitoring it. We're going to make sure we get that. And last but not least, please be sure to fill out your survey. Even if you don't want this shirt, it's a pretty cool shirt. You can give it away for Christmas or something like that. But what you want to do is let us know how we're doing, good or bad. We want to make sure that we hear your feedback, but do it soon. What I've noticed is people do their surveys at the end of the week and they forget. They've seen 20 sessions and they may confuse people, and we see that a lot. So make sure you understand to fill your surveys and you can get participation for that. And always continue your education. Spend time to meet the engineer. Go to the World of Solutions. We have a lot of good stuff and innovation out there for data center networking and across other domains as well within Cisco. And make sure you can understand what you can actually have to your education, and make sure that you continue learning at the Cisco Live event. So thanks again for coming today. I really appreciate your time, and enjoy the rest of your day. Hopefully this is a good start of the day. Thank you.